Thanks. Yeah, my name is Aaron Parecki. I'm a developer advocate at Okta. But yeah, I'm going to talk about OAuth today. This is my Twitter account and my website. Feel free to tweet me questions or stuff afterwards. I also maintain OAuth.net, which is the sort of home of OAuth on the internet. It's essentially a pointer to things. There's not a lot of actual content on it, but it's a good reference of if you're looking for information, it's a good home, which will then send you out to places that actually have real information, but it kind of organizes everything around OAuth. This is the book. The talk tonight is essentially some section of the book in verbal form, but the book goes into much more of this in detail. So let's get started. Before we start talking about OAuth and how OAuth works, I want to start with a bit of background about why we have it in the first place. It's helpful to understand where it came from and understand the motivations of why it was developed and the problems that it's intended to solve. This pattern, you may remember from many years ago, although as recently as 2010, Facebook was actually doing this. Back when Facebook was relatively new, or any app was a new app, you would sign up for an account, and then it would ask you, hey, let's go see if any of your friends are also using this app. And it would ask you for your email address, and then it would ask you for your email address password.
Oh dear.
Oh dear is right. That is the appropriate reaction. And it wasn't just like random sites doing this. It was like Facebook. You'd expect better from them. It would then go log into your email, and then download all your contacts, see if anybody else who is in your address book is on Facebook, and then be like, hey, we found a bunch of your friends. Cool, we'll go ahead and send an invite to them. This is obviously terrible for many reasons. For one, in order for this to work, the app has to have your password and then likely store it, because in order for it to actually use it more than once, it's going to have to put it somewhere, and it has to put it somewhere in a plain text or recoverable format. When the app has your password, it can do anything to your account. It could not only download your contacts, but it could send email for you, right? If this was Gmail we're talking about. There's no way to turn off that access once you give it your password, except by changing your password, which is, who wants to change their password, right? If the app was compromised, which happens, database leaks happen all the time, now that means your password is essentially out there. It's not just a hashed version of your password either. It's your actual password. So this was terrible, but apps were doing this, and clearly this demonstrated that there was a need for this pattern of giving some application access to your account. A lot of companies got together who were building websites and web apps and platforms for people to build on top of, and decided to solve this problem, and essentially worked together and standardized what they were experimenting with and developed what became OAuth. This was from 2007 to 2012 or so was when all this work was moving very quickly and being developed. So what ended up coming out of that effort was a community-driven effort, was OAuth, which is a framework, not technically a spec, which I'll get into later. It's a framework that allows users to authorize apps to act on their behalf or access their data. What this ends up looking like is you see a screen like this now. If you click a login with Twitter button, you get taken to Twitter. Twitter asks for your password, which is fine because it's Twitter. And then you go back to the app, and then the app has access to your Twitter account. Same with GitHub. GitHub shows this app wants to do such and such to your account. It's going to have access to this, this, and this. The thing that OAuth doesn't give is actually information about who logged in. So OAuth just gives access. It doesn't actually provide identity information. So in that way, it's like hotel keycards, where when you go to the front desk, you get a keycard. But then you take that keycard to the hotel door. The door doesn't care who you are. It doesn't know who you are. All that it knows is that the keycard that you're holding has access to this door for this limited period of time. So that keycard is like an OAuth access token. It doesn't actually say who you are. And that is the difference between authentication and authorization, which you hear a lot and is sometimes confusing, but it's an important distinction. And OAuth was meant to solve the authorization part, not the authentication part, and it's a little unfortunate that both of these words start with the same 4 letters, which is also the name of the spec. So, oh well, here we are. That's why it's confusing. So to start out, we're going to talk about OAuth clients and developing an OAuth client. So everything that I'm talking about for this first part will be from the point of view of writing an app, talking to an existing service. The way that, or at the end of the sort of OAuth dance or OAuth flow, or however you want to call it, the end result is that the application gets an access token. And there's a bunch of different ways that this can happen, but the end result is an access token. In OAuth terminology, we talk about applications use an OAuth flow to obtain an access token. And there are different flows for different use cases. So the authorization code flow is the most common. It's for web apps and native apps. There's the device flow, which you see on browserless devices like the Apple TV or Roku devices. There's also a password flow for OAuth. We'll talk about that more later. There's the refresh token flow. But at the end of all of these flows, the app has an access token. It then uses that access token in a HTTP request. It puts it in the authorization header. And then that server can then check the access token to see if it's valid and process the request. So to get started, as a developer building an app, you first have to go to the service that you're working with, GitHub or Google or whatever, and register an application. Registering the application, first it'll make you sign up as a developer and agree to like the developer terms of service. But then registering the application gives you a client ID. The client ID is the public identifier for the app. If the application is not a public client, which I'll define in a minute, you will also get a client secret. If you're building a web app using the authorization code flow, you will get a client ID and a client secret. These two things together, these identify the application to Google or GitHub or whatever the OAuth service is. A public client is an application that can't keep strings secret. So you have things like JavaScript clients, because as a user of a JavaScript app, you can open up the browser, hit view source, and then see all the source code of the app. Even if it wasn't literally embedded in the source code, the app is at some point would have to use a secret, and it is accessible because of the runtime environment of JavaScript apps. Same for native apps. Native apps that ship code to the user, they can be decompiled, and you can extract a string out of it. So for these, we just don't use a client secret, and there are other techniques that provide the security that the secret would have otherwise provided. So we're going to start with web server apps. These are the most common you see all the time, and this is also the authorization code flow is kind of the basis of the rest of them, and everything is kind of based around that. And I have a couple different ways of looking at this, and I find that people have different styles of learning, so bear with me as I kind of repeat the same thing a few different times in different ways. So we're going to start by using this visual diagram to illustrate the different roles involved. We have the user sitting in front of a computer, so that's going to be the user agent, is what the browser is called in this terminology. Then up in the top right, there's the client or the application, and then there's two pieces to the OAuth service. There's the authorization server and the resource server. The authorization server is the thing that users go to log in, grant access. The resource server is like the API. It's the thing that has the data. In this example, there's Google has done a pretty good job of building out a very wide range of services all contained under one authorization server, so I like to use them as an example. If you've ever noticed when you're logging into stuff, like even if you log into YouTube, you end up on accounts.google.com, where you type in your Google password, and then you go back to YouTube. And that's because they've routed everything through their one authorization server. So the user starts out by going to the application. The application sends them to the authorization server. After this redirect that happens, the application then talks to the authorization server directly, and then it gets an access token that it can use to access the API. So that's the high-level overview. Here's the step-by-step version of that. So the person in front of the computer says, hey, I'm going to use this cool app. They're on the app's website, and there's like a login button. The app says, great, please go to the authorization server to let me have access. The user then gets sent to the authorization server, accounts like google.com, for example, and in that URL, there's information that essentially says, I'd like to log into the best app ever. It wants write access to my account. The authorization server says, cool, here is a temporary code that the app can use to get access. The user then takes that code, gives it to the app. The app takes it, sends it to the authorization server, which then sends the application an access token. And then the application can use the access token to make requests. And there's a couple of important things in here. Note that in this flow, the access token doesn't actually end up in the user's browser. It's on the web server. This is why it's the authorization code flow for the web server app. So let's walk through this. This is the login link. So the user is using this great app and is going to click this button that says login. The app builds up a URL with a bunch of parameters in the query string. First is response type is code, which tells the server we're doing the authorization code flow. It includes the client ID, which identifies the application. It includes the redirect URI, which tells the authorization server where to send the user back to after they've authorized the app. It includes a scope, which tells the server which parts of the account the application wants access to. It also includes the state parameter, which is a security check that the app will do later. So that ends up looking like a URL like this. The user clicks this and is sent to the authorization server, which presents a prompt saying, hey, this app wants to access your account, description of what the app is requesting. If the user allows that request, it'll redirect back to the application with that code and the state. And if the user denies it, it'll redirect back with an error. At this point, the application has to verify the state matches the state it set originally, and this is a little security check for the application's sake. And then it takes the code and it exchanges it for an access token. So in order to do that, the application, now this is running on the web server, makes a call directly to the authorization server. It's a post request with a bunch of parameters. Grant type is authorization code. It has the code that came from the query string. It includes the redirect URI as well as the client ID, and it also includes the client secret. And this is because this is the code running on the web server, which is not, the source code of this is not accessible to the user, so it has a secret that it can use for this. It makes the post request to the server, and the response is an access token, as well as the expiration time of the access token and a refresh token. Or if there was a problem with the request, like if it was missing a parameter or if it took too long and the code expired, it'll get back an error. So the last way I want to look at this is another sort of visual step-by-step of what we just saw. The user is looking at this app and it says, connect with Google, log in, whatever that button's called, builds up that URL with the response type as code and all the parameters. They get directed to the authorization server where they log in and see the request to authorize the application. The server then sends the user back to the app with the code and the state. The app sits there and behind the scenes is making a post request back to the authorization server to get an access token. So that's the step-by-step of the authorization code flow. The other important thing in this diagram, it's kind of hard to tell, but that middle line is green. That represents in what we call like a back channel, where that request was not made by the user's browser or a device in the control of the user. It was made from the server. So it includes the secret, the client secret. And that, because it's a back channel, because it's not made from a thing that's in control of the user, that information, the application can essentially trust it because it knows it's talking to accounts.google.com and it knows the response came from Google and was not intercepted. Whereas in this bottom step, this redirect was sent over the front channel, which is the user's browser. And this is essentially, Google is sending the user back to the app, but anybody could just make a URL, give it to a user that looks like that, and the app would like try to do something. So that's why we have this state check and other things like that. So in general, the front channel and back channel distinction is important. The application can trust data sent over the back channel, and it should very strictly check anything it gets over the front channel. So the next flow I'm going to talk about is the implicit flow for JavaScript apps. So JavaScript apps can't use a client secret because they just don't have a way to conceal that from the user. In this case, the browser is both the application and the user agent. It's performing both roles, so there is no back channel. There's no actual like security. The application can't even trust that it's running the right code, essentially, right? So there's no way to use a secret, so we just don't. And instead, we have this implicit flow. It looks very similar to the authorization code flow, but it's actually a lot shorter. We start by saying response type is token. We include the client ID and the redirect URI and the scope and the state. This is all the same as the authorization code flow, except for the first one is response type is token instead of code. Build up this URL. The user clicks it. They will see the prompt like before. And then they'll get redirected back to the application with either the token or the error. The difference in this case is that the token is sent directly. This is the access token. This is not the temporary authorization code. It's the actual access token. And it's sent in the fragment instead of the query string. So it's a hash sign. And the reason for that is because browsers don't send anything past the hash sign to the server when they make a request. It just sends everything before. If it was in the query string, the user's browser would send the access token to the server, which can't do anything because it's essentially just serving static files. So we don't want it in like access logs and over the wire at all. So in this case, the app just gets the access token directly in a way that only the JavaScript on that page can access. Note there is no code exchange, there's no secret. It's a much simplified flow. It also means that you don't get any benefits of the security check of using the secret or having that back channel because everything was sent over the front channel. Which brings me to, there are very, very limited circumstances in which this makes sense to use. If the server supports it, a better option is to use the authorization code flow and just not send the secret, because you essentially don't lose any security over the implicit flow, and you avoid a few of the problems that the implicit flow provides. I have some more information on that on this page on OAuth.net, which links to that long URL, which has a lot more information on it about when it's appropriate to use it and more about the security implications of that. It's worth a read if you're interested in the details of that. I will also say that in the context of OpenID Connect, the threat model is very different, so it's in many cases okay to use it there, where it would be something that you would actually want to avoid in OAuth. So happy to answer more questions on that at the end, but I'm going to leave that there for now. So the next use case I want to cover is mobile apps. And mobile apps, like JavaScript apps, also can't use a client secret. The other big difference between mobile apps and browser-based apps is the way that redirect URLs are handled. With a browser app, with an app running in a browser, we have DNS, we have HTTPS, certificate authority chains and all that, which means that when the application is redirecting the user back to the app, it can be reasonably sure that the user is going to get back to the app that the server thinks it's sending the user to. So if you have an app running at exampleapp.com and the authorization server is like, cool, here's a code, or here's an access token, or here's a code, I'm going to send you back to the app to go ahead with that, it can be pretty sure that it's not sending the user to an attacker's app. Of course, there are, like, if you're in an enterprise network where your DNS has been screwed with, as well as like you've been man in the middle by your corporate IT, then yeah, there's some issues there, but for the most part on the public web, certainly consumer web, DNS protects against that kind of stuff. With mobile apps, you just don't have that, because there is no DNS for mobile apps. There's no actual registration of custom URL schemes. Any app can just make up a URL scheme and say, hey, I handle example : / and if two apps decided they handle the same thing, then whichever one's installed will get the request. And there's no way for the server to know like whether that's what app's gonna handle that request. There's also like the app claimed URL patterns, where an app can register a domain name or URL pattern or segment to match against. For the most part, I believe Android and iOS have some sort of registration or verification before they will ship an app that claims, like Google.com. Like, you can't just go and make an app that says you handle all Google.com URLs, but it's also like the kind of thing that you're pretty much just counting on Apple and Google to check that. So you can't really ever be 100% sure as like the authorization server that you're actually going to send the user back to the right spot. So to solve these problems, we have this extension to OAuth, which is called Pixie. It's essentially an on-the-fly client secret, that's how I like to describe it. And it provides the security that a client secret provides almost for mobile apps, although you can actually use it in JavaScript apps too. It's just most servers don't set you up for that yet. The way this works is it adds a step to the beginning and to the end of the authorization code flow. So before the app gets started, before it generates the URL to send the user to log in, it first generates a random string, and it has to be between 43 and 128 characters long. It then computes the hash of that, and we're going to call these strings, the plain text string, we're going to call it the verifier, and the hash we're going to call the challenge. Then, when it builds the login link, the first authorization URL, it's going to include the hashed string and tell the server what hashing method to use. And I think that's just so that in the future we can change it to better hashes. And then, at the end of the flow, when the app is taking the code and exchanging it for the access token, instead of using the secret, the app sends the plain text and the verifier. And that way, what ends up happening, and remember how I mentioned the front channel and back channel? So with the mobile app case, the hashed version is sent over the front channel. So anything that intercepts that only has the hashed version. And the code exchange happens over the back channel, where the app is making an HTTP request to the server rather than going through a browser. And it sends the plain text, which is going over HTTPS, so it's not going to get like hijacked or anything. And that way the server knows that, this is why I said it was like kind of like a dynamic client secret, because then the server can hash it itself and check, did that hash match the hash that came through the front channel? And that matches up the request. So this ends up looking like, let's generate a random string. Let's take the hash of that and base64 URL encode it so it is friendly to deal with over the wire. The first bunch of lines, the lighter shaded lines, are the same authorization code request that we saw at the beginning, and then we've added these two parameters to it. Now the rest of this, the user doesn't see anything different. They're going to see the authorization request on the mobile app, just like they did before. The redirect back is the same as before. There's nothing additional sent in this part. And where it differs is when the app goes and makes that post request. So it's going to build the same post request that it did before, with the grant type as authorization code, the redirect URI, and the client ID. And then instead of the client secret, it's going to send the plain text string that it used to generate the hash. So that is like I said before, that's because that's going over the back channel. The app is making the HTTP request itself. It can trust that the plain text code is being sent to the server not messed with. Nothing's going to grab it. And then it can check, the server checks, does the hashed version of that match what was sent over the untrusted front channel. And then the app will get back the access token and probably also a refresh token in this case. Luckily, if you're using a server that supports this, you don't actually have to worry about any of that if you just use this library. So OAuth.io is, it's basically Google's packaging up of this spec as code that you can use. And so if you're talking to a server, it doesn't have to be Google. If you're talking to a server that supports Pixie, you can just use this native app library, and it handles more than just Pixie. It also handles like the particulars of opening up browsers on the different platforms, depending on the different versions that are supported, because there's a whole bunch of different, between iOS like 8 and 11, there's a bunch of changes of how you can launch browsers and the security contexts of them and all that. So this just like wraps it all up in a nice little library. So it's thankfully you don't have to actually know too much about the whole Pixie thing underneath if you just use the library. Okay, so the next flow I want to talk about is the password flow. And I want to talk about it because it is named as one of the official flows in the OAuth spec. However, it is not actually a very good idea to use it except in very limited circumstances, because in order for this to work, the app has to actually have the user's password, which was like one of the whole things we were trying to avoid in the first place with OAuth. But the reason it's useful is because if you are making your own app for your own service, like if you are Google and you make actually Google's a bad example because they just send everything through their OAuth server. But if you're Twitter, right, and you are shipping a Twitter native app, it is completely not surprising if the user sees a password prompt asking for your Twitter password in the Twitter app. Right? Fine. The benefit of doing the password flow with OAuth is that remember how I said the end result of all these flows is an access token? The same is true for the password flow. The app sends the username and password to the server, gets back an access token, and now it can proceed this exact same way as any other app that uses the platform. You don't have to worry about a separate mechanism for dealing with sessions or user identity or anything. So you get to piggyback on all the existing infrastructure that you would already have to manage logins and authorizations. The next flow is client credentials, which is meant for server-to-server communication. This one's even shorter. It's just these 3 parameters in the request. You send the grant type and then the client ID and the client secret, and you get back an access token. Note that there is no user mentioned in this because this is meant for server-to-server access where the app is accessing its own resources. So that might be like the app is getting a list of users who've authorized the app, or the app wants to update its app icon. Something where it's not accessing users' data, it's just accessing its own resources. And again, by using this mechanism, you get to piggyback on all of the existing security and the rest of the infrastructure you've got around your OAuth server. Okay, now for a fun one. Browserless devices. So these are things like Apple TV, Roku, Amazon Fire Stick, things that don't actually have a web browser in them. Or things like this device on the right, which is like it's a hardware video encoder. So you can actually like plug in a HDMI source into that and then push video out to Facebook or YouTube. In order for that to work, these don't have a browser, so you can't do normal OAuth on them. So instead, there's this device flow, which is, of course, an extension to OAuth. And it's a pretty clever solution to that problem. And I'm sure you've actually interacted with it at some point before. So the way this works, the app first starts out by requesting a device code and user code. And it just makes a post request to this new endpoint with its client ID. And again, because this is these are devices shipped to the user, you can't actually put secrets in them because they can be decompiled or extracted or whatever. So you just use a public identifier. The response to that post request is a very long string, device code, a short string called the user code, a URL that the user is going to go open up in some other device, like their phone or their laptop, as well as this interval, which is how often the device should check this to see if the user has authorized the app yet, and how long this is valid before it'll have to start over. So the device starts out by showing the URL and the user code to the user somehow. And that's up to the device how to do that. In the case of this little device, it has a 3-line LCD screen, so it can actually print out the URL and the device code. If you go to google.com/device, you will see this screen. And you can actually try that right now. You'll see this screen. You type in the device code. In the meantime, this device that you are attempting to authorize, it's going to make this post request to the token endpoint with the grant type as device code and the client ID and that very long string that it didn't show the user, just held on to that. And it's going to make a post request every 5 seconds or whatever that interval was. While the user is doing this on their phone, they're going to get back this response that says authorization is pending. So you first enter the short user code. Then Google asks you, cool, okay, that checked out. Now please sign in. However, you've connected if you're on like a Google hosted domain, you do the 2-factor auth. So app's waiting. And then it says choose which YouTube account you want to authorize. And then finally, you see the OAuth prompt that says, this device wants to manage your YouTube account. And if you click allow on the phone, you're just done. You just stop there. It says, great, go back to your device. And in the meantime, the device is sitting there polling, and eventually it'll get back this access token. And then we're back to the way that everything else works. You have an access token, and you can make requests now to the API. So it's a pretty clever solution to how do you handle authorizing a device that you can't open a web browser in while like making a pretty not terrible experience for the user. You see this on Apple TV when you log in like to your HBO account. You'll do the same thing. You go to like hbo.com/device on your phone. You choose your cable provider and authenticate that way, and then eventually the phone is like, cool, you're done. Go back to your TV, and the TV then continues. The one downside to this is that it's a little bit of extra work for the user compared to like a normal OAuth flow, because they have to type in a URL as well as this like 6 or 8 letter code. And it's not terrible. They've done a pretty good job of making that relatively easy. There's like recommendations around the character set for that code, which is like don't use I and L or 1, just like don't. Use all the other letters because there's plenty of other letters. Don't distinguish between caps and lowercase. Make it super easy to not mess up that entry. But it's still a little bit more to ask the user to do that. So there's a couple of people working on extensions to this, or like alternate flows of this to make that more seamless, which would be like essentially using a separate channel to send that URL and the user code to the phone. So you can imagine like NFC, if the device could activate a thing where you then tap your phone and the browser opens to that URL where it's already pre-filled, then you only have to log in on Google or whatever, which is QR code. Or QR code. Take a picture of a QR code if it can display QR code, or maybe even it's Bluetooth and it's like, anyway, there's a whole bunch of different ways this could work. So people are experimenting with that, and we'll see something interesting come out of that, I'm sure. Yeah, cool. Okay, so the very last flow is the refresh token flow. And in a couple of these, you've seen the app gets an access token as well as a refresh token. The refresh token is a special token, and the only thing it can do is it can get new access tokens. So the access token will usually expire after some amount of time. That amount of time is defined entirely by the authorization server, as well as like policies that it may have around which device you're using or which user group you're in or whatever. Twitter's policy is access tokens never expire. I think GitHub's as well. Access tokens just never expire. But like in enterprise situations especially, you end up with very short-lived access tokens, like maybe just an hour before they expire, and then the app has to get a new access token. And instead of sending the user back through the whole flow again, it can use this refresh token to get one without the user's interaction. Sometimes the service will make the application specifically request a refresh token by requiring a certain scope. It's not always the case. Sometimes servers just return it automatically. Usually servers don't issue them to JavaScript apps because of the higher security risk that those pose with the implicit flow or just in general. Also, JavaScript apps tend to be only used when the user is in front of the computer and not, the user doesn't expect that the JavaScript app will continue to run when the user is not in front of the computer. Technically, it's possible now with service workers, so maybe that may change, but for the most part, people are using a browser and they expect the token to only last as long as they're in front of it. So to use the refresh token, the app just makes a request with grant type is set to refresh token. It includes the refresh token as well as the redirected URI that was used originally to get that token, and the client ID and the client secret, but only includes the secret if it has a secret. So a native app would not use that. If for some reason a JavaScript app was able to had a refresh token, it would also not use the secret. It'll get back a new access token in the response. It may get a new refresh token, it may not. That is not defined by the spec, so servers just do their own thing on it. Essentially, as an app developer, you have to just sort of roll with the flow in this, and if you get a new refresh token, assume that that's the next one you should use next time. If you don't get a new refresh token, assume that the one you had before will work again. But there isn't, there's nothing in the spec about that, so read the docs, I guess. And you may have noticed that at several points during this, I've said things like, the spec doesn't say what to do, or servers may do this differently, and that's because it goes, again, back to why OAuth is a framework more than a spec itself, because it really is more of just, here's a pattern that you can follow to do this kind of thing, rather than specifying exactly how to do it. In practice, most servers made the same decisions, which is, again, why I wrote this book, because most of the things are actually the same, and there are very limited circumstances in which they differ. So I've collected all those best practices into the book. But yeah, there's definitely some holes that you have to if you read the spec, you'll eventually realize there's a bunch of holes you have to fill in with your imagination. Which takes me to part 2. So the whole first part was about building applications as an app developer talking to an existing service. There's a lot of things that we breezed over really quickly because the service just made their own decisions and provided you a thing to use. If you are building an OAuth server, you have to make even more decisions about that. I'm going to talk about just a few of the high-level or user-visible decisions that you make as an OAuth server and things that you need to do if you are building out an OAuth server. So to start, you need to provide a way for your developers to register applications. And this is GitHub's registration screen. GitHub asks the developer for the application name, the URL for the homepage of the app, a description of the app, a icon, and then most important on this screen is the callback URL box on the bottom. So registering the app is a way for the service to associate a client ID and a redirect URL together so that it can only send user to trusted URLs. In addition to registering clients, the service should also have a way to unregister or delete the application if the developer doesn't want it anymore, which means things like revoking all the active access tokens that were granted to that application. The service is also going to issue a secret to the app if it's a web app, which means it needs a way to display that to the user or to the developer, possibly also have a way for the developer to go back in and retrieve the secret. Some services show you the secret only once, and they're like, if you lose this, you're screwed. You have to make a new one. Some of them will let you like click a button, type in your password again, and then it will show you the secret. It's entirely up to the service to how to do that. Yeah, so there's a whole bunch to this aspect of registering applications, and you kind of like don't really think about it as a developer of an app. You just like go through the steps that the service presents to you. But if you are the service, you're going to have to think through all these steps. So during the authorization step, when the application has sent a user to the authorization server, we kind of took for granted that the user was already logged in when we walked through a bunch of the examples. But if the user is not logged in, you need to authenticate them, which is the first step you have to do before you can authorize the application. So with Google's a good example. You always end up on accounts.google.com. You enter your email address or your phone number. I've never signed in with my phone number before, but I guess you can. You have the forgot email or forgot password flow as part of this. If you've configured two-factor auth or a single sign-on through a custom domain, that's part of the authentication process when the user logs in. From the application's point of view, it never sees this happening. It just sends the user out, and then they eventually come back. But the server itself is going to have to do all the actual authentication of the user. The actual authorization prompt, and then if the service supports multi-factor authentication, you have to, of course, provide your users a way to enroll those factors. So, like with the YubiKey, plug it in, enroll the thing. And this is like not part of it. This is not a spec thing. This is not even part of OAuth. It's just a part of authenticating users to your service. But you have to authenticate users to your service when you're building an OAuth server. So it's an important thing to note, to remember that you're going to have to build that. The actual authorization interface itself has a couple of components that are important to point out. So this is like a mock-up I made, but they all have the same primary components. So you have the service, Google or our example service. You have the name of the third-party app that was registered when the developer made the app. You have it's usually a good idea to provide the actual name of the developer that registered the app. Oh, I keep forgetting to add the screenshot to this slide. A couple months ago, I think it was actually in the fall, Google's OAuth screen did not include the name of the developer. It only included the name of the app, and they didn't check. You could just type in anything as the name of the app. So somebody made an app called Google Docs, and then sent out links saying like, "Hey, so-and-so shared a file with you. Please click this button to view your file." And they would click, and they would end up on Google. And it's not quite a phishing attack, because they end up on the real Google, and then they authorize the application, which is called Google Docs. And the end of this is this attacker ends up with an API, an access token to your Google account that was completely legitimately obtained. And there was no like hack, there was no redirect spoofing, there was like, it was pretty clever. But the real solution to that was put the name of the developer on there, because, and like the website they put in, because, well, and hope that you don't let your developer say that you are Google as well. But yeah, pretty clever. So yeah, identify as much as you can about the application that is being given access. Show which user is logged in, because people often have many different accounts. And if you end up on Twitter and you're like logging into the Twitter app, and then suddenly you end up back and you're in the wrong account, you want to give people a heads up before they authorize an app to the wrong account. List the scopes the application is requesting, and I have more details on that in a bit. And then, of course, the allow and the cancel buttons. After users have authorized apps, you should give them a way to view which apps have been authorized, as well as let them revoke those apps. This is what GitHub looks like. So if you like dive into your GitHub settings, you'll end up seeing a screen like this, which will show you all the applications that you've authorized. And it's a good idea to review these periodically as a user, because you've probably logged into a bunch of different apps that you've forgotten about by now, because it may have been like 3 years ago that you logged into some like, hey, let's graph your GitHub activity and show you a fun graph thing, which can probably still access your account. GitHub's is pretty nice because it actually tells you when the last time the application accessed your account was. So you can see if it's actually continuing to access, or if it's like last used 2.5 years ago. Cool. That's good to know that it wasn't like continually downloading my information when I forgot about the app. If you click on one of the apps in GitHub, you actually see more details about that, what the app has access to. So it actually tells you all of the scopes and permissions that the app has, as well as a nice big red revoke button. This is Google's version of the application authorization list. So I like this one because it has a nice, like, friendly plain text summary of the scope. It's kind of hard to read, but Google Chrome, for example, has full access to your Google account. Hangout Toolbox has access to Google Drive, Google Hangouts, and basic account info, which means it does not have access to YouTube, for example. IFT has some account access, including, so they have this like nice little plain text versions that are not super intimidating. If you click on them, you then get a lot more details about exactly which services it has access to, when it was authorized, and again, a remove button. This is Twitter's. Twitter's is just this one list, but it says the permissions it has, as well as when it was approved. So scopes. Scopes are a big part of OAuth. Scopes are a very powerful concept. As far as the spec is concerned, scopes are left up to the service to define. It just the spec just says that scopes have to be string separated by spaces if you're going to provide multiple. But the actual values of those are not standardized. So as the developer of the service, you get to define what scopes you're going to provide your developers and your users. Typically, a good place to start is just read versus write access. So that way applications can request only read access, and when users are logging into those apps, they don't have to worry that an app's going to be able to update information. Another good way to do it is to restrict access to sensitive information, whatever that means to you. For example, on GitHub, that might be private repos. Apps have to specifically request access to private repos, which is good because I know that there are, like if you're working at a company and you want to just like log into some random OAuth app on your personal account, but your personal account has permissions on the company's account, you can't like even legally make a, grant access to some other company, grant access to your company's source code to some other company. So thankfully GitHub has that separated out. By functionality, so Google does this by like Google's services, so Google Drive, YouTube, Gmail, those are all considered separate functionality, separate resources, so they all have different scopes, and they all have scopes within those as well. Billable resources is a good idea to split on as well. If your API has some actions that will actually cause the user to be billed like more than what they would otherwise be billed, maybe don't allow apps to use that by default. Make sure that the app has to actually request it so that the user knows that the app is going to be able to make them pay money. Amazon is a good example of this, where you can launch EC2 servers using the API. So maybe when I'm logging into some thing with my Amazon account, that should have to explicitly request to be able to launch EC2 servers, and not just like random thing that's going to analyze my shopping history, be able to spin up servers and mine Bitcoin, because that's never happened before. When the service is actually going to present the scopes to the user, there's a tricky balance to strike here between providing the information about the scopes without overwhelming the user. So you want to make sure that the users actually understand what is being granted to the application, but you don't want to give them a wall of text so that they just click OK. This is Google's. They've gone through many iterations of this, and this is a pretty good solution. So they have couple of interesting components here. They show the icon of the service that the scope represents, as well as a short text, like English sentence of the request. Presumably it's localized as well. And then this little I button. And if you click the little button, then you get the wall of text of, oh, like, what was that about Google Drive? Oh, this is exactly what it can do in Google Drive. And now they've requested details, so now you can give them details. The other cool thing that that the spec itself allows, although many services haven't actually taken advantage of it, is that just because an application requests certain scopes doesn't mean the service has to grant those scopes. This is a mock-up of Twitter, and Twitter never actually went through with this, but they did hire the guy who made the mock-up. This was back when like Twitter apps were going crazy by like you would tweet out like, hey, I'm ranked such and such, or I have this many followers or whatever. But it tweeted that without the user really realizing it, because they just clicked this thing that was like analyze your friend list, and then it would go and like post out and then a link to that, and then it would go viral because everybody was seeing all their friends tweeting about how cool they were or whatever. So the idea with this is if the app is requesting to be able to post tweets, let the user uncheck that box so that you can still use the app, but it just can't post for you. Facebook actually went and implemented this. So if you click, if you end up on an OAuth prompt on Facebook, you'll see a prompt that is pretty simple like this, but then it says edit the info you provide. And if you click that, you can then actually go and you see all of the scopes that the application is requesting, and there's a checkbox, and you can then revoke certain ones. Fitbit went and did checkboxes quite literally, but it works pretty well. So if an application wants access to all of your Fitbit data, you'll see a screen like this, where it's going to list all of the scopes. But you can then go and uncheck any of them, and you can be like, nope, I don't want it to access my weight or sleep. And if you click allow, it'll still go back to the app and it'll grant an access token. It's just the access token won't work for the weight API. So that is that's the end of the server section. Like I said, there's a lot more to it than that, and that was like the high-level overview. I have a few links to other places you can go to find more information. OAuth.net, it's the home of OAuth on the web, but it's also a good bouncing off point. There's also OAuth.com/playground, which I made last year, which it's basically like an interactive walkthrough of all the flows. So it steps through each of the grant types, as well as OpenID Connect, and it talks to a real server, and you can see what's actually happening step by step. It'll like show you the requests being made and actually grant you a real access token at the end. There's also this book, which I will give a few copies of here, and during the quiz portion of the evening. And yeah, that's it. Thank you very much.